Hello students, this is Mr. Allen. Today we're going to look at section 7.3, which is on proving that triangles are similar. Our objective today is to use something called the AA, the SAS, or the SSS similarity theorems to prove triangles are similar. Now we're not talking about congruent, we're talking about similarity. We also want to be able to figure out how to find the measurements of things indirectly. So our first postulate, and this is probably the most important one, because if we can use this one, it's a very easy thing to use to prove because there's only two requirements. And it's called the AA similarity postulate. If two angles of one triangle are congruent to two angles of another triangle, then those triangles have to be similar. So in this triangle on the left, if angle S is congruent to angle M on the triangle on the right, and if angle R is congruent to angle L in the second triangle, then those two triangles are what we call similar. As we can see, they are not congruent in this case, but they are indeed similar. So that means they have the same shape, but not necessarily the same size. So let's look at example 1 here. It says, are the two triangles are similar, and how do you know? So let's go ahead. I'm going to move myself up here. So let's look at the first one. Well, we know that angle R, we know that angle R is congruent to angle V because that angle is congruent to that angle. It'd be nice if we could find another pair of angles that are congruent, and the good news is we can see that. We know that this angle, angle WSR, has to be congruent to this angle here, angle VSB, because they are vertical angles, and we know that vertical angles are congruent. So therefore, we can conclude, and I'm going to write a similarity statement. We can say that triangle RSW is similar to triangle VSB. Now, please keep in mind that whenever we make a similarity statement, we need to make sure that corresponding parts are lined up. So, for example, angle R was congruent to angle V, so you'll notice that angle R and angle V are the first two letters in those similarity statements. Now let's go and look at the second two triangles. Are those guys similar? Well, not sure. It's obvious, I think, and let me use a different color here. Let's use blue. It seems that that angle, well, I don't know. That one isn't paired up with one that I don't see a 30 over there, but okay, I see a 70, so let's do the 70. So we can see that angle L and angle R are congruent because they are both 70 degrees. But I don't know, 30 and 85 aren't clearly the same. Let's see if we can figure out what angle K is. So 30 plus 70 is 100, so that means that angle K here has to be 80 degrees. Now guys, if these two triangles are similar, that means that all of their corresponding angles have to be congruent. And 80 clearly does not equal 85, so these are not similar. There's no way that they can be similar. These are not similar. Okay, let's go ahead and move on. Next example. Okay, theorem SAS. So this is very similar to our SAS congruence theorem that we used in chapter 3, I believe. And here's what this theorem says. This theorem says if you have a pair of angles that are congruent, I'm going to start with the A part. And by the way, the A is in the middle because it has to be the included angle. Now here's where this is different. Now notice the S and S piece. So what it's saying is if AB is proportional to QR, or the same ratio, if you will, and let's say AC is, and again, I'm making up numbers here, let's say that AC is 1, and then let's say that QS is 2. If those corresponding sides are proportional, then these two triangles are similar. So let's say that angle A is congruent to angle Q. We know that 2 is to 4 as 1 is to 2. Therefore, the two triangles would be similar. So that's the SAS. You can probably guess what SSS stands for, side, side, side similarity. Here we need all three pairs of corresponding sides to be in the same ratio, or what we call proportional. And again, these numbers aren't accurate, but let's say, if this was 1 and this was 2, and let's say this was 2 and this was 4, and let's say this was 3 and this was 6. Obviously, all three of those. So you'd have 1 is to 2, S2 is to 4, S3 is to 6, and they're all equal, obviously, to 1/2. So that's the SSS. So we've got the AA, which is the easiest one. We have the SAS, which is side angle side, and SSS. Now, when we're dealing with sides, we're not trying to necessarily show that they are the same measure. They just need to be proportional. Now, they could be the same measure. So let's look at example 2. Are these triangles similar? If so, write a similarity statement. So let's see here. We've got triangle. Well, let's see. I'm going to go with the longest. It looks like this appears to me that if they're going to be similar, we're going to have to use SSS because we don't know any of the angles of the triangles. So I'm going to put 10 is to 15. Now that was the longest and the longest. Does that equal? Let's go to the second longest. So that'd be 8. The second longest over here would be 12. And then the third longest would be 6. And then 9. Now do all of those equal each other? So one way we could do this is just cross multiply all of them. But the other thing we could do is just simplify. And I'll do that maybe in a different color here. 10 over 15, that's the same thing as 2/3. Because 5 goes into 10 2 times, 5 goes into 15 3 times. 4 goes into 8 2 times, 4 goes into 12 3 times, and then 2. Yep. So those are indeed proportional. So these two triangles are similar because of SSS. And now we're supposed to write a similarity statement. So here's where we got to be very careful. Now I'm going to go with this angle here because it looks kind of almost like a right angle. So I'm going to say triangle TUS is similar to triangle. Now T pairs with V, so V has to be next. And now we got to be careful. So I picked U, this one right here is my second letter. So notice I went from the right angle to the second longest side. So I'm going to need to go this way on this one. So this is going to be WVWX. So there's my similarity statement, and they are indeed similar. All right. Next one, we've got overlapping triangles. So what I might do is I'm going to highlight this triangle, and what I'm going to do is draw a separate triangle. I'm going to pull this triangle MKN out separately. Okay, so this is K, this is M, this is N. We know that this whole length here has to be 10 because 8 plus 2 is 10. The bottom length has to be 15. Oh, I guess we should also note that that angle has to be congruent to that angle. So this may be SAS, but we got to check. We've got angle K is congruent to angle K, and that's by the reflexive property, right? We know that. We know that. Now let's see if our sides are proportional. So we got to see, does KL, is it the ratio of KL to KM? So that's this side, the KM length, to the length. So we're talking about the side on the left here. Remember, we're talking about the small triangle, KLP, and big triangle, KMN. We're going to see if KL is to KM over what, KN. All right, so let's see. Now let's go ahead and put in some numbers here. Let's do that in a different color. We'll just do that in light blue. KL is 8. And then KM is 10. And then KP is 12. And then KN is 15. Now, I'm going to show you a different way to check to see if they're proportional, and that's just to cross multiply. And I'm going to use my calculator to do that, so I'm going to cross multiply these. So I'm going to do 8 times 15, so that's 120. So I multiplied these two guys together. Now I'm going to multiply the other two guys together. That also turns out to be 120. So they are indeed proportional. So these guys are going to be similar by the SAS similarity postulate, and our statement of similarity is going to be a little bit easier on this one. It's going to be triangle KLP is similar to triangle KMN. So there's our similarity statement. Okay, now let's do a little proof here. That's what this, I'm going to move that down so we can see that triangle. So we have two triangles here. We're trying to prove that they are similar. And I've already got the proof kind of started, a skeleton proof, and we just need to fill in some blanks here. So we know that those two pairs of segments, oops, I think I just messed that up. Not sure what I did there. Oh, it's like doing text here now. Okay, that's fine. I don't want to see that though. Okay, anyways, we know that FG is congruent to GH, and KJ is, or JK is congruent to KL. That's given. So we've got our pictures marked here that those are congruent. Now we just need to figure out why those two. Oh, that's just the definition of isosceles triangles. So we know that these are isosceles triangles because the definition of an isosceles triangle is that the two sides have to be congruent, and we have two sides are congruent, so that's great. Now, statement 3, the reason is that the angles of the isosceles triangle are congruent. So let's see here. F would have to be congruent to H, and J would also have to be congruent to L. So I'm going to write angle F is congruent to angle H, and angle J is congruent to angle L. It's angle L there. Angle L is kind of in the way there. That's by the basis of isosceles triangle are congruent, or what I would call ITT. We also know that angle F is congruent to angle J because that was given. Now, number 5 says the transitive property of congruence. So I claim that in this, so if we're doing transitivity, so that's going to tell us basically angle F is congruent to angle H, is congruent to angle J, is congruent to angle L. All of those angles are congruent by the transitive property of congruence. And so therefore we've got what we needed, that these two triangles are congruent by the AA similarity postulate. It's been a while since we've done a proof. That's kind of fun. All right, our last slide here, our last example. So part of what we want to be able to do is obviously prove triangles are congruent, but we also want to be able to apply this knowledge, and we can do that doing this thing called indirect measure. So here we've got a guy standing down below this cliff. He knows his height, and he wants to figure out the height of the cliff indirectly. Okay, so what he's going to do is he's going to use similar triangles. So you can see that we have triangle. In fact, let me point them out here. We've got this triangle here. This is triangle HTV, and I claim that that triangle is similar to triangle JSV. And you can even see in the pictures that we've got the two right angles, and then we've got the two congruent angles. So those are going to be congruent, or I'm sorry, similar because of AA. So they're similar because of the AA similarity. So we know that they are similar. Now what we can do is we can use the fact, since they're similar, that means that their side lengths are proportional. In other words, TV is to SV as HT is to JS. Okay? So the bottom of the left triangle is to the bottom of the right triangle, as the vertical distance of the left triangle is to the vertical distance of the right triangle. So look carefully. So now we can go ahead and convert that, and I'll use a different color. Well, what's the length of TV? Well, TV, I think, is 6. SV is what, 34, just plugging in the numbers off the picture. HT is 5.5, and JS is X. Now we can go ahead and cross multiply, and I'm going to use my calculator to help me do that. So 6 times X is 6X, that's easy. But now I need to do 34 times 5.5. I don't know what that is off the top of my head. Turns out to be 187. So now we just need to divide that by 6, and I get 31 2/3, and we'll say feet. So there's X, 31 and 0.667 feet. So, and that'll end our presentation for today for proving triangles are similar.